We'll start with some relatively simple examples, then we'll consider more complicated ones, and then we'll move on to other topics. So, the first problem today is like this. Suppose x to the x plus y to the x is equal to 2. Line y prime of x and y double prime of x at point 1, 1. So we are given a function y which is defined for us explicitly in terms of just an equation that it satisfies x to the x plus y to the x is equal to 2. And the question is to find the first derivative and the second derivative of this function at the point 1, 1. Well, as we discussed last time, actually y is not really a function. If you want to know this curve, the curve is defined by this equation, looks somewhat like this. Kind of a rounded square like this. We have a point 1, 1 right here, and we want to find the slope of the tangent line and the second derivative. So if you look in the small area of this point, you do get a function, and the question is, what is the derivative and the second derivative of this function? Okay, so does anyone remember how we started such questions from last time? Say it over.
So you take the derivative with respect to x and y and then on both sides. Basically you take the derivative on both sides and then so it becomes 5x to the power 4 plus 5y to the power 4 of dy dx by 2.
Okay, yes, perfect. Indeed. The first step is, well, we have a relation on x and y. And this relation is given by this equation. Well, next I want to find the relation between x, y, and the derivative. To do this, I apply the derivative to both sides of this equation. On the left side, I have, well, derivative of x to the 5 is 5x to the 4th. Derivative of y to the 5 is 5y to the 4th. And remember that y is a function of x, it's not just a variable. And you find derivative relative to x. So it's from the chain rule, it's 5y to the 4th times derivative of the argument, derivative of y. And on the right side, I have derivative of 2, which is 0. So here I have relation between derivative x and y. Okay, very good. Now I find dy by dx, which is isolated. And I find it as minus x to the 4th over y to the 4th. And now I can plug in the number. At the point 1, 1, this derivative is minus 1 divided by 1, so it is minus 1. Okay, so that's basically just what we did last time. Find, well, given an equation, find derivative of both sides, isolate the derivative, and plug in the numbers. So we answered the first question. The second question is, what is the second derivative? How to go about the second derivative? this thing, right? Yes, exactly. So how to find the second derivative? Well, I already have the first derivative. The second derivative is just derivative of the derivative. So find the derivative of this expression. So for y double prime of x, well, let me take this expression dy by dx and apply d by dx. By the way, we do have a notation for second derivative like this. It's d squared y divided by dx squared. It's just the same thing as the second derivative notation. So what I'm saying, the second derivative is the derivative of the first derivative. And I do know what is the first derivative. It is minus x to the fourth over y to the fourth. The remaining part is, well, just find this derivative. It's given to me as, the expression is given to me as a quotient, x to the fourth over y to the fourth, with a minus sign. I will apply the usual quotient. So it's minus derivative of numerator, which is 4x cubed, times denominator, y to the fourth, minus the numerator, x to the fourth, times derivative of denominator. Recall that derivative of y to the fourth is 4y cubed times derivative of y. Once again, it's important to remember y is not just a variable, it is a function. Divided by y to the fourth, denominator squared. Well, from here we have two options how to proceed. One option would be, so let me actually write option one. We found some expression for the second derivative, but it does involve the first derivative. So one option would be, well, let's take this first derivative and plug in what we already know about. Minus x to the fourth over y to the fourth. And then we'll find that the second derivative of y is minus 4x cubed y to the fourth plus, because of minus sign, x to the fourth 4x to the fourth y cubed times derivative, which is minus x to the fourth over y to the fourth, and everything divided by y to the eighth, and then plug in the numbers. The second derivative at the point 1, is minus 4 plus 4 times minus 1 divided by 1. So it is negative. So it's a good way to proceed, especially if you later are interested, for example, in finding the third derivative or something like this. If you're actually interested in the second derivative for any point x, any point xy, then it's a good idea to plug in the expression for the derivative which you already know. Another option would be, well, already here, let's try to plug in 1, 1. So that's a good option. Another one would be and directly plug in the numbers to this expression. I will get minus 4 times 1 cubed 1 to the fourth minus 1 to the fourth times 4 times 1 cubed times dy by dx at the point 1, 1 divided by 1 to the fourth squared. So just plug in the numbers. Notice the way to write it. I don't, well, I mean, when I was looking at the midterms, I noticed that a lot of you do the following thing. You find the expression, say, for second derivative, then you want to plug in the numbers, and you just write equal, and then some numbers. Well, that's wrong. You can't just go from a function to its value at a point. They are not equal. A function is a function, value is a value. You have to start a new line and to say, well, the value of the derivative at the point 1, 1 is such a thing. It is important. You can't just put an equality sign and continue. Okay, anyway. But here we still have this unpleasant thing, the value of derivative at the point 1, 1. But the good thing is we already know it from the previous computation. It is -1. So we can continue. It's minus 4 minus 4 times 1 divided by 1/8 is to 78. Well, maybe let me comment on one more thing which could go wrong. You should not find the second derivative by first plugging in the numbers into the first derivative and then trying to take the second derivative. That would be just meaningless. The second derivative is derivative of the first derivative, not the derivative of the value of first derivative at some point. So be careful to derive the correct expression. Okay, so any questions about this? Yeah.
How do you go from negative the one above it? Yeah, the negative in the middle.
Yes, from
The
here to
positive.
here. So
Oh, you move the
for
negative.
Hammond, this sign was a sign in front of the whole fraction.
Oh, it's
And then it's what it means is negative of the whole expression.
okay.
Yeah.
We substitute d over dx with y prime, d squared of y over dx squared with y double prime.
Yes. So it's you can do this. I don't know a good notation for how would it denote second derivative at the point 1, 1. So probably if you wanted to use the notation y double prime, you would have to write something like this. And inwards when x equal to 1 and y equal to 1, y double prime of x is something like this. With this notation I just have conventional notation of how to plug in a point, and this one I don't. So we have to work around. Other questions? Okay. Maybe another comment. There is another way to find the second derivative. Not exactly this way, but just already here you found the relation between x, y, and the derivative. Take this, well, apply the derivative once again to this expression. It would also work. So maybe I'll write this option 3. You have an equation on the first derivative, x to the fourth plus y to the fourth divided by dx is equal to 0. If you are interested in the second derivative but not really interested in the first one, so you don't want to solve for divided by dx for some reason, well, apply derivative once again. You'll get 4 q plus, here you have product 4y q times dy by dx times another dy by dx. This one coming from the chain rule, differentiating this one, and this is that one, plus y to the fourth times the second derivative. And then you see that you can isolate the second derivative. So find this first derivative from this equation and second derivative from that equation. That would also work. But that cannot finish this computation, it will still be the minus 8. Yeah. So here I was trying to differentiate y to the fourth times this thing. I apply the product rule, and then in the first thing I differentiate y to the fourth and leave this as it is. So this goes to here, and this expression is derivative of y to the fourth. So this expression is derivative of y to the fourth. It's 4y cubed times the derivative of y. Other questions? Yeah. Is the question, how did I go from here to here? I just divided by 5. I mean, here I have an equation of the form y times something is equal to 0, so it means that this something is equal to 0. I mean, if you don't want to divide by 5, just don't divide by 5. It's a matter of percentage. Okay, so let's try a more complicated example. Before we talk about the next example, let me talk a little bit about a small piece of geometry which will be relevant for us. It's about the condition when two lines are perpendicular. So when are two lines given by some equations, perpendicular. You also say orthogonal. So the question is like this: you are given two lines, two equations of two lines, and how do you understand that they are actually perpendicular to each other? How do you find out that the angle between them is exactly 90 degrees? Okay, so the answer turns out to be like this: m1 times m2 is -1. So not quite reciprocal, -1. Let me explain this answer. So it turns out, well, naturally, this only depends on the slopes, not on the actual position of the line, just on the slope, on the direction. So the two directions should be perpendicular to each other. Let me explain a little bit why it is true. Let me draw a picture. have a line with slope m. It means that for every one step to the right, I make m steps upwards. That's what it means to have a line slope m. What does it mean to rotate it by 90 degrees? Well, when you rotate it by 90 degrees, this movement to the right becomes movement upwards. One. And this movement upwards by m becomes a movement to the left by m. And then I have the line at 90 degrees. What is the slope? Well, it's a change of y. So if this has slope m, this will have slope change in y, which is -1, divided by change in x, which is m. So it's -1 over m. So you see from this very simple consideration that two lines are orthogonal to each other, perpendicular to each other, if and only if the product of their slopes is -1. Well, it will be useful for us because we'll discuss now a normal line to a curve. If you have a curve, sometimes it is useful to discuss not just the tangent line, which you already are pretty good at finding, but also the normal line, the one which is perpendicular to the curve. For example, in physics, when you have an object moving along a curve, you might want to decompose its velocity into two components. One which is tangent to the line, and one which is orthogonal. The part which is tangent to the curve is kind of propelling the object forward along the curve, and the one which is perpendicular is actually changing the direction. It's the one which is responsible for this body not to go in a straight line, but rather in a curve. So in some situations it is useful to talk about normal line. Okay, so let's try to solve an example with this. Find the tangent and normal lines the curve three x squared plus y squared is equal to 25 x squared minus y squared to point -2.1. So here's the complicated expression. It defines y as a sort of function of x. Well, not exactly a function, but at least locally a function. And we are interested in the tangent direction at this point and the normal direction, the one which is perpendicular to the tangent direction. Maybe just to have a picture on the board, I'll sketch how this curve looks like. It's not required for solution of the problem, just out of curiosity. It looks like this. So if you try to sketch all possible x and y which satisfy this equation, that's exactly the curve that you get. And our point, negative 2, 1, is a point somewhere here. And the question is find the equation of this line, tangent line, and find the one which is perpendicular. Okay, so let's start solving. And basically you know what to do. We want to find the derivative first, to find the slope of the tangent line, and for this we should differentiate both sides of this equation. So we start by applying the derivative to both sides of the equation. Well, might be a little bit tricky because it's a complicated expression, but let's do it slowly. We should differentiate 3 times this thing squared. So what is the derivative? It's obviously a composite function. It's 3 times something squared, and this something is itself a function. So let's apply the chain rule. Derivative of squaring is 2 times the argument. So I'm not done yet of course. I just different. Guys, if you have questions, please ask me. I mean, probably because because many of you are talking at the same time, probably many of you have questions. So if you have a question, ask me. I will answer to everyone. But if you start talking between yourself, it means that most of the other people just don't hear. So don't be afraid to interrupt me, but please do be afraid to just talk. Okay, so I'm trying to differentiate this expression. 3 times something squared. The derivative is, well, 3 times 2 times the argument, well, times the derivative of the argument itself. So times the derivative of this expression, x squared plus y squared. So I want to find the derivative of x squared plus y squared. What is the derivative? Well, derivative of x squared is 2x. Derivative of y squared is 2y times the derivative of y itself. Okay, so that was the derivative of the left side. With the right side, probably it's even easier. I have just 25 times derivative of this expression. 25 times 2x minus 2y times the y by dx. Okay, so we found this relation between x, y, and the derivative. Next step would be isolate the derivative. I'm interested to find this derivative. Let's try to isolate. It doesn't look as simple as it used to be in previous questions, but it's not that terrible either. We can try to open the brackets and move everything with the derivative to one side and without it to the other side. So let me open the brackets. And first I will divide by 2 on both sides. And now I'll open the brackets. So 6 x squared plus y squared times x plus 6x squared plus y squared times y times the derivative is equal to 24x minus 25 x squared plus y squared times the derivative. So next I will move everything with the derivative to one side, without it to the other side. So again, did I make a mistake? Yes, I did make a mistake. So there it was just 25y. Should be just 25y. Sorry. Totally wrong. Okay, so I move everything with the derivative to one side, without it to the other one. So I get dy by dx times 25y plus 6 x squared plus y squared is 25x minus 6 x squared plus y squared. So now I can finally find the expression for the derivative. Dy by dx is 25x. And did I make another mistake? Yes. So here it was 6 times this times x. Okay, so it is 25x minus 6 x squared plus y squared times x divided by another mistake. Wow. So here it was 25y. No, here it is 6x squared plus y squared times y times dy dx. So I'm missing the y here. Okay, let me rewrite this line once again so that everyone will have correct with the notes. 25y plus 6 x squared plus y squared y. Everything multiplied by derivative is 25x minus 6 x squared plus y squared times x. So the derivative dy by dx is, well, let me factor out x. X times 25 minus 6 x squared plus y squared. And in the denominator, I factor out the y. 25 plus 6 x squared plus y squared. So I'm sorry about this kind of lengthy calculation, but so that's what it turns out to be. So the derivative turns out to be this expression, x times this divided by y times that. Okay, so even though the computation was a little bit long, the essence was still the same. We started with the equation, we found its derivative of both sides, and then we isolated the derivative. This. Okay, now we can plug in the number. Dy by dx, when x is negative 2 and y is equal to 1, is this negative 2 times 25 minus 6 times 5 divided by 1 times 25 plus 6 times 5. So it's minus 2 times minus 5. So it's 10 divided by 55. So it's 2 over 11. So the slope of this line, of the tangent line, is 2 over 11. So probably it's a little bit less steep than this in this picture. But anyway, we found this slope. that's not quite what we were asked. We wanted to find the actual tangent line. So the tangent line well, I now know its slope, and I also know a point on this line. Of course I do. It's the point at which I'm trying to find the tangent. It's minus 2, 1. So the line that passes to the point negative 2, 1 and has a slope has such an equation. Difference in y values is the slope times difference in x values. So now we have our answer. Tangent line has the equation y is 2 over 11x and c plus 4 over 11 plus another 1, so plus 15 over 11. So I basically used just the fact that we found the slope using the implicit differentiation and we know a point. Next part, I want to find the normal line, the line which is orthogonal, which is perpendicular to this line. So what should I do?
Take the inverse and set it to the negative slope, and then solve for its
Yes, so the first thing, for the normal line, I'll find the slope. The slope, well, we know when two lines are perpendicular to each other, but the product of the slopes is negative 1. So to find the slope of the perpendicular line, I should just take this number, invert it, and take the minus sign. So it's minus 11 over 2. But now to find the actual line, it's as easy as it was for the tangent line. I still have the same point on this line. Still negative 2, 1. So equation would be y minus 1 is negative 11 over 2 times x minus negative 2. So normal line is y is negative 11 over 2x minus 11 plus 1, so minus 10. So now we can improve this picture a little bit. We can put the numbers. So I have the point negative 2, 1 somewhere here. The tangent line has small slope, and this intercept point is 15 over 11. The perpendicular line is like this. This is negative 10. And the curve, well, something like this. So this angle is 90 degrees. Okay. So, any questions up to this point? Maybe the most complicated, I mean, it was about the same set of ideas, finding derivative of equation, finding derivative of both sides of equation. It was just technically a little bit more complicated problem. The equation was more complicated. Okay, let's go to part B, which is about vertical tangents. Find the points on curve, the same curve, 3x squared plus y squared squared is 5x squared minus y squared, where the tangent line is vertical. Last time we actually have seen such kind of problem. We realized that what does it mean for the tangent line to be vertical? Well, say again, x equal to 0.
No,
Well, in this case, no.
the
I mean, something is 0, but the denominator is 0. Right. So, if the tangent line, well, let's start with this observation. If any line has, well, is vertical, what is its slope? It just doesn't exist. The vertical line doesn't have any slope. It's not of the form y is equal to something plus x plus something. It's of the form x is a number. Or you can think about it this way. A line which is horizontal has slope 0, a line which is kind of 45 degrees has slope 1. So here you'll have slope 2, 3, 4. As the slope increases, the line becomes more and more vertical. The actual vertical line, you can see it has kind of infinitely large slope. You can't, I mean, if you move one step to the right, you'll have to move infinitely many steps upwards to actually go exactly in perpendicular direction. So, if the tangent line is vertical, then dy by dx does not exist. And that's a very general observation. If you want a tangent line which is vertical, the derivative at such a point should just not exist. How does it translate to our problem? Well, in our problem we know this expression for the derivative, i.e. x times 25 minus 6 x squared plus y squared divided by y divided by 5 plus 6 x squared plus y squared does not exist. But there is only one way how such an expression might not exist. Only if the denominator is 0. So here the denominator must indeed be 0. 25 plus 6 x squared plus y squared must be equal to 0. Well, the rest seems to be just algebra. You have to solve such an equation, and it's in fact very simple one. Y times something, well, product of two things is equal to 0. It means one of them is 0. So y is equal to 0, or 25 plus 6 x squared plus y squared is equal to 0. Let's actually leave this. Okay, one of these two options is actually very easy to analyze. This option. So if 25 plus 6 x squared plus y squared is equal to 0, how is it possible?
The 6 bracket x squared plus y squared has to be equal to negative 1.
Okay, and how is that possible?
That means that formula is like a circle formula. So you will have a root. So you can solve those roots.
I mean, well, you're close. I mean, so you say that this equation describes kind of circle with a negative radius. But what is it? Well, it's not really an object. So maybe a simpler way to put this would be, it just never happens. This number is always strictly positive. If you take 25 and add to it sum of two squares, well, it's still at least 25. So we get no solutions. Because 25 plus 6 times x squared plus y squared is at least 25, which is definitely strictly positive. So what actually interests us is the other case, y is equal to 0. So if y is equal to 0, well, it's still not the only equation that we should solve. We should solve two equations. One is y equal to 0, which guarantees that this denominator vanishes, that this denominator is 0. And the other condition is that the point x comma y is in fact on the curve. So this equation. And 3x squared plus y squared is 25 x squared plus y squared. We should solve both equations simultaneously. Once again, this equation is responsible for the fact that the derivative does not exist. The second equation is responsible for the fact that the point should be on the curve. Okay, now we can quite easily solve it. We just plug in y equal to 0. So we get 3x to the fourth must be equal to 25x squared. Or I can factor it as x squared times 3x squared minus 25 is equal to 0. Or, well, which means, once again, product of two things is equal to 0. It means that one of them is equal to 0. So x is equal to 0. Or the other option is 3x squared is minus 24 is 24. 3x squared is 24. Okay, 25. So we get three solutions. In one of them, x is equal to 0 and y is equal to 0. And the other two is x is square root of 25 over 3, y is 0. And the third one is the same thing but with minus sign. So we did some algebra, and we solved this equation when the denominator over there is 0 and the point lies on the curve. It turned out that we get three solutions. But let's now stop for a second and see what we actually found. Did we actually answer the question that we wanted? Did we find the points where the tangent line is vertical? Well, let's see. Our argument started as follows. If the tangent line is vertical, then, well, something happens. As a conclusion, something else happens. As a conclusion, something else happens. And the final conclusion is the point is such or such or such. So let me repeat what I just said. We showed that if the tangent line at the point xy is vertical, then xy is one of the following. 0, 0, square root of 25 over 3, 0, or negative square root of 25 over 3, 0. That's what we showed so far. Question: is it actually what we wanted? So the question is, well, we just showed that if the tangent line at the point is vertical, then the point is one of the three. The actual question was find all the points where the tangent line is vertical. So did we answer the original question? Well, let me once again remind you how the picture looks like. And what are the points that we actually found? Well, two of them, this one and that one, are located right here. Here the tangent line is indeed vertical. At least it looks like. At the origin, well, it doesn't look like we have a vertical tangent line. Something quite different happens. There is no contradiction. What we showed is that if the tangent line is vertical, then the point is one of the three. We did not show that each one of these 3 points has a vertical tangent line. No, we didn't. We only showed that if the tangent line is vertical, then we must be at one of the 3 points. But one of them turns out to be kind of, well, what is it? False positive. It seems like it might be a point where the tangent line is vertical, but actually, no, it isn't. Let me show you how the algebra works here. Why two of these points we have one phenomenon, and in the third one we have quite different phenomenon. Well, look at this expression for the derivative once again. Indeed, at each one of these 3 points, the denominator is 0. But let's look also at what happens at nearby points. So if x, let's say, is not exactly square root of 25 over 3, but just close to it, and y just gets close to 0. What happens to this closure? So I have this part. If you compute what happens to just this part, it approaches some particular number. So x approaches this value, x squared plus y squared approaches 25 over 3. So this thing approaches minus 25. This thing approaches plus 50. So this thing approaches something like minus square root of 25 over 3 divided by 2, I would say. I'm not sure about the arithmetic. But anyway, it approaches some some non-zero number. And then you take this number and divide it by something which is very small. what kind of answer do you expect to get? Well, if you take a non-zero number divided by something small, you're going to get a huge number. So at nearby points, the slope is actually huge, actually almost vertical, which is very reasonable. That's exactly what happens here. At such points, I have huge positive slope. At such points, I have huge but negative slope. Same happens if here I have instead of plus sign a minus sign. It's just here I have a different number to which this whole thing approaches. But let's look at the other point, 0, 0. What happens there? So when x approaches 0 and y approaches 0, what happens to this dy by dx? Well, we have this quotient x over y, and the other quotient 25 minus 6x squared plus y squared, 25 plus 6x squared plus y squared. Well, part of this expression doesn't have any problems. This whole thing approaches 1. But the other part, x over y, does have a problem. What is it? It's a quotient of small number x by another small number. But we know very well that quotient of two small numbers is just an undefined quantity. It really depends how large is each one of these numbers relative to the other one. It could be that one of them is, say, 0.1 and the other one is 0.0001. And then it really depends which one is the first one and which one is the second. The quotient might be either small, large, or in fact anything in between. So this thing, which looks kind of at the point 0, it's a quotient like 0 divided by 0. At nearby points, it's still not defined. Still small number by small number. So that's what prevents this expression from being actually something. It's not a large number, it's not a small number, it's nothing. And we see it right here. If it were something, some actual number, it would have been the slope of the tangent line. But we don't have one. We have two. We have one tangent line like this and another one. So even though this curve is kind of very nice, very smooth, you can trace it without any sudden turns. Still, at this point, you have kind of self-intersection. And here you have not one tangent line, but two tangent lines, two different tangent lines. And the algebra confirms it. You see that the algebra tells you, well, my best guess as to what happens at this point is that I don't know, 0 divided by 0. The algebra just doesn't know. I mean, it's not that there are no ways to actually analyze this situation and find the actual slopes of these tangent lines. It's just more complicated than what they are going to cover in this course. But what I wanted to tell you, basically, is such a thing. If you want to find, say, vertical tangent line, well, what you should do is find the points where the derivative does not exist. But you should also remember that derivative might not exist for several reasons. One is indeed the vertical tangent line, like here or here, but there are several others. One is a self-crossing like this, where you don't have just one tangent line, but several of them. And yet another one, the one which we are familiar from usual non-differentiability, the corner. So such a thing also can happen, and here you also might not have a derivative. Okay, so any questions about this one? So the question was whether the full answer is this one or should we remove the 0, 0. So I would say we should remove 0, 0. Because if the question is where the tangent line is vertical, well, after really good really hard thinking, we understood that here and here it is vertical, but here the derivative doesn't exist very differently. So actually the answer would be tangent line is vertical. Only at plus or minus the root of 85 over 3 over 0. So only two answers, not three. But that might be also a little bit beyond what we ask in the course. So what we actually ask here is just for you to understand that there are several reasons why the derivative might not exist. One of them, maybe the most kind of probable, is that actually you have a vertical tangent line, but there are several others. Self-crossing like this, or a corner like this. Okay, so let's move to another topic. Let me try something, and then I'll do something which is halfway between being right and wrong. So I would say food for thought. Suppose I want to differentiate such an expression. Y is negative 2 to the power x. Well, there isn't really any problem with differentiating this expression because we know how to do stuff with, one thing to the power of another one. We can apply logarithm, make it much simpler, and then apply differentiation. Okay, that would work. So let's apply logarithm. 1 of y is 1 of negative 2 to the power x. Well, what is 1 of negative 2 to the power x? It's 1 of negative 1 times 2 to the power x, which by the rules of rules of logarithm is 1 of minus 1 plus x times 1 of root. And now we can find the derivative. Apply d by dx to both sides. And we find on the left side derivative of logarithm is 1 over y times y prime. On the right side, 1 of minus 1 is just a number, so its derivative is 0. 1 of 2 is also a number, so derivative of 1 of 2 times x is 1 of 2. So we get that y prime is y times 1, 2, or negative 2 to the power x times 1, 2. Okay, I hope that this looks very familiar and very simple. I mean, we did such examples last time. We did much more complicated examples. This should be really, really easy. But I did write that that there is something wrong with this. Does anyone see any problem with this computation? Yeah. Exactly. So I went from here to here, and I already made a mistake. What mistake I'm talking about? Well, 2 to the power x is always a positive number. 2 to any power is still positive. negative 2 to the power x is negative. So even though this expression is always defined, logarithm of this expression is never defined. Just doesn't exist ever. And then I made another mistake. From here to here, I went, well, from logarithm of negative 2 to the power x, I transformed it as logarithm of negative 1 plus something. What is logarithm of negative 1? Is there some number such that e to the power of this number is negative 1? Well, of course, no. So this number does not exist. But somehow in the end, well, it does look that I got an answer. And in fact, if you try, if you try to actually differentiate, this answer is correct. So there is something kind of funny going on. I applied the wrong procedure, but in the end I did get the correct answer. So there are two ways to actually make this calculation correct. One way is kind of what advanced mathematics does, and that's, well, logarithm of -1 or logarithm of negative numbers doesn't exist kind of in our usual numbers, but there are special numbers for complex numbers for which it does exist, and this calculation works. Well, for this approach you'll have to study, well, at least another year to actually justify it. In this course we'll take another approach. We'll take another approach. Recall what we did when we discussed the derivative of logarithm. Well, the derivative of logarithm we claimed was 1 over x, and this formula works for x which is positive. Let me try to find logarithm derivative of 1 of minus x. First of all, does it even make sense? Well, yes, it does make sense, but only for x which is itself negative. When x is negative, minus x is positive, and then, well, the expression makes sense. So that would, this calculation would hold only for x which is negative. Well, let's find what this derivative is. Let's apply the usual chain rule. It's logarithm of some expression in terms of x. So it's 1 divided by the expression times derivative of the expression, which is -1. And we get a surprising result. It's still 1 over x. So both this function and that function have the same derivative, 1 over x. But for one of them, the result is weighted for x which is positive, for the other one for x which is negative. So let's combine these two functions to form just one function. How? Well, let me take logarithm, but now not of x, but rather absolute value of x. Why is it good? Well, when x is positive, I'm just taking 1 of x. When x is negative, I just remove the negative sign, so I'm taking 1 of negative x. So in fact, when x is positive, I'm talking about this function. When x is negative, I'm talking about this function. Let me make the write down. It's ln of x when x is positive. It's ln of minus x when x is negative. And then we just prove a funny result. Derivative of this complicated function, ln of absolute value of x, is exactly 1 over s. And this result is valid for both x which is positive and x which is negative. Basically for any x which is not equal to 0. Well, let me sketch this function. it's the usual logarithm when x is positive, and it is 1 minus x when x is negative, so it looks like a reflection of the same thing. And the derivative, well, it has the properties that you would expect. Here it is obviously positive and decreasing. It looks like this. Here it is negative and still decreasing. And it looks like this. So it's a good thing to remember such a property. That 1 of absolute value of x is derivative, just like the one for 1 of x, but now it's waiting for any x. Well, let's now revisit this example. Let's make a calculation which would actually work. So, revisit this y is equal to negative 2 to the power x. So, yes, I can't really apply logarithm to both sides, because one of the sides is, well, both sides are negative. This thing is a negative number. Yeah?
I don't understand the ln absolute value of x, the graph. I thought every x would be positive. So there,
No. X can be whatever number it wants to be.
yeah,
Absolute value of x will be positive number.
yes.
But logarithm can be both positive and negative. Logarithm of numbers which are greater than 1.
Yeah, why do you have the other side?
So when x is negative,
Yeah.
say minus 5,
Yeah.
what happens to this function? It computes absolute value of negative y, which is 5, computes the logarithm, and outputs this value. So at this point it is 1, 5.
Oh.
Other questions? Okay, so I would like to apply logarithm here, but I can't. This expression is negative. So instead I apply this formula, this function, ln of absolute value. Ln absolute value of y is ln of absolute value negative 2 to the power x. And what's good about it, the absolute value doesn't care about the negative sign. This is the same as ln of 2 to the power x, which is x times ln 2. Well, now let's differentiate both sides. D by dx on both sides. Well, derivative of ln absolute value of something is 1 over this something times derivative of y is derivative of x ln 2, which is ln 2. Conclusion, y prime is y times ln 2, so it is negative 2 to the power x times ln 2. So now we get basically the same answer that we got in the previous computation, and it is the correct answer. But now we have also a valid way to get this answer. This actually works. So this way, well, it doesn't really work. It does produce the correct answer. So, but it is much better to do it this way, because, well, now you can be sure that it actually works. You can justify every single step. Y is negative 2 to the power x. Okay, maybe the final example for today will be such a figure. Find dy by dx at the point 4, 2 if y is defined by the following funny equation. X to the power y is y to the power x. Well, it happens sometimes. For instance, if x is the same as y, of course x to the y is the same as y to the x. But also at some other points it happens. When x is say 4 and y is 2, we see that 4 squared is the same as 2 to the power 4, and both are equal to 16. So such equality holds sometimes. So, well, the set of all points x and y which satisfy this equality forms some curve, and the question is, what is the slope of tangent line to this curve at this point 4, 2? Well, and we know what to do. We have a dependence between x and y. We should differentiate implicitly. We should differentiate both sides. The problem is how to differentiate such a thing. It is x to the power of some function of x. Ln, exactly. So before we differentiate this, we already see it will be hard to differentiate this. Instead, let's apply logarithm first. So solution goes like this. Apply ln. If you want to be kind of extra safe, you might want to apply ln of absolute value. It doesn't really matter in this case because, well, x and y are both positive, so no problems. Let's just apply logarithm. And then we get ln of x to the power y is the same as ln of y to the power x, which we can rewrite as y ln x is equal to x ln y. Well, next step, let's apply derivative to both sides. We want to find some relation between x, y, and the derivative. Okay, so when I find the derivative of the left side, I apply the usual product rule. So it will be derivative of y times 1 of x plus y times derivative of 1 of x, which is 1 over x. On the right side, I will have derivative of x times 1y plus x times derivative of 1y. Derivative of 1y is 1 over y times y prime. Okay, now it's really easy to find what y prime is. We just isolate it, it's y prime times 1x minus x over y is 1y minus y over x. And you get that dy by dx is 1y minus y over x divided by 1x minus x over y. So at the point 4, 2, you get the derivative is 1, 4 minus 4 over 2 divided by 1, 2 minus 2 over 4. So basically, why I wanted to give this example is not really because of the particular computation or particular numbers, or even because of this very funny equation. It's because sometimes we don't want to apply implicit differentiation to the original equation. Sometimes we want to transform it. And one way to transform it to get a simpler equation is apply logarithm. So in this way we combine logarithmic differentiation and implicit differentiation. Okay, and maybe last announcement, next week on Thursday we'll have a quiz, and the quiz is going to be on chain rule, implicit differentiation, and logarithmic differentiation. So everything up to now.